So 6b is measures of dispersion, and this is a measurement of how spread out data items might be versus the measurements of central tendency, which tell you where the centers or where data tends to clump. So to demonstrate the limitations of just measuring centrality, let's look at the example we've got below. We've got two different data sets. We're asked to find the mean, median, and mode for each of these data sets. Mean, median, and mode for the two data sets. And well, let's have a look at it. So the mean of this data set is pretty easy to come up with. We just calculate, add all the items up just like we normally would. I think we have 6 sevens total, that's right. Add them all together, divide by 6. This is 42 over 6, which is 7. So the mean is 7. The median of this data. Okay, so the median is the center value in the list when the list is arranged from smallest to largest or largest to smallest. In this case, they're all the same size. It's going to be obvious that the median's probably 7, but if we realize we have an even number of values here, 6 sevens, the middle two are the third and fourth, so we need to use those middle two to calculate the actual median. If you have a middle 2 instead of a middle 1, you have to take the average of the middle two. You add them up, divide by 2. Our median's 14 over 2, and that's 7 again. Okay, the mode of this data set, that's the most obvious one. There's only one number that occurs for the values in this data set, and that's 7. Okay, so mean, median, and mode were all 7 in this first data set. Okay, so let's compare that to the one below, the second data set. So again, the mean calculated the standard way, sum all the items up, and we'll divide by their count. Their count is 6, there's 6 data items, and that's going to be again 42 over 6, which is 7. So the mean is 7 in this case. These two data sets are different. We have 3 4s and 3 10s versus 6 sevens, right? These are obviously different sets of numbers, but their mean is the same. The next thing we'll see is their median. Well, the list is already arranged in smallest to largest, so we need to find the middle. In the middle, since we have 6 data items, we have a middle 2 instead of a middle 1. If we had an odd number of items, we'd just pick that single data value that's in the middle. So since we have 2, we'll do 4 plus 10, divide by 2. Again, we take their mean. The mean of the middle 2 is the median. 14 over 2, and that's 7. So I think we're starting to see the point here. If we look at mean and median for each of these data sets, even though these data sets are different, they have the same mean and the same median, which that goes to say to some extent that measures of central tendency don't quite tell us everything about a data set. Where we do start to see a difference, maybe they aren't fully clear about what they can tell us, but we could see some differences. The mode is actually different in this case. We've got 3 4s and 3 10s. There's a tie for the mode. It's 4 and 10. It goes to both of those. Okay, so it wouldn't be until we calculated the mode that we realized that these two data sets might actually be different. Otherwise, mean and median could be pretty misleading as far as how these data sets are different. So measures of central tendency can only tell us so much. We need to get some idea of measuring how spread out data is. We'll have two measurements for that. The first is the range. The range is literally just the difference between the highest data value and the lowest data value. So we just find the highest value on the list, subtract from it the lowest value, and we've got the range. It's a pretty easy calculation. So, looking at the list of data we've got here, looks like we have test grades, and we're asked to calculate the range of these test grades. 94 appears to be our largest value. 57 is our smallest. So our range then is highest minus smallest or lowest, or largest minus smallest, 94 minus 57, and that gives us 37. So the range is 37. Okay, so that starts to give us some measurement in terms of how things are spread out, and it's kind of an obvious one. Taking the lowest value to the highest value tells you what realm of data, what range across the number line our data can occur at. So it doesn't quite tell us, though, what the average, in some sense, space between data items is. In other words, if we were to arrange them, what's the average step from one data item to the next? So that's what the standard deviation actually does for us. And this box is included in the notes. It's from the textbook. It's there just to demonstrate what the steps are to write it out. You probably don't have to consult it every time. If you want to build a table like what we're going to see on the next page, you can build the table to calculate the standard deviation. But a couple things I'll point out here. X bar is the mean of the data, so we'll refer to that quite a bit in what's to come. We have the deviation from the mean of each data item. That's this x minus x bar. For every data item x on our list, we're going to subtract from it the mean x bar that we'll have calculated. Right? Then we'll square all of those. Then we'll add all of those up. The sum of all these squared deviations is what that'll be called. Sigma, again, remember that's the sum. Sigma is the capital letter sigma, Greek letter. And after we sum up all those data items, we'll divide by n minus 1. Remember that n is the count, or it's the number of data items. It's just like it is in the mean. Okay, instead of dividing by n, though, we divide by n minus 1, just one small adjustment. And the very end, we take the square root of all of that. So that's a walkthrough of the formula. I think if you use the steps on the next page with the example, you have a clearer idea of what to do. Also, a lot of calculators online can help you check your work or just simply calculate this for you. Okay, so we're given a list of numbers here. We've got, looks like 9 values right here. And this problem actually writes out the steps for us. You won't always have that given to you, but for now it's a nice place to start. You can construct it on your own if you'd like. Okay, so the first thing we need to do, step 1, we need to calculate the mean of these data items. We have 8 plus 7, so we list them all as a sum. And we divide by n in our case. Like I said, we've got 4 and 3, that's 7 data items. N is 7 actually, when we count them all up. Okay, so we divide by n, which is 7, taking the mean the normal way. And the number we get from this is, the mean will be 7. Using a calculator, nice to have around. Now for the table, sometimes this left column will be filled in. The values 8, 7, 9, the list of values that you're given to find the standard deviation of will be input into this table already. If not, you could always build it on your own and work from here. Okay, the next step. This is the deviations from the mean. It's this x minus x bar. This deviations from the mean. It's literally 8 minus 7. Okay, so I'll write the first one in just so we've got it. But we'll say 8 minus 7, and that's 1. Now as we go down the list, I'll just fill them in. We've got 7 minus 7 is 0. 9 minus 7 is 2. 7 minus 7 is 0 again. 7 minus 7. 4 minus 7, negative 3. Write it exactly as we see it. And then 7 minus 7 is 0. Okay? Now we square these deviations in the next column. So as we come over to x minus x bar squared, we'll have 1 squared, which is just 1. And we keep going. 0 squared is 0. And I'll leave off with some of these. 2 squared is 4, of course. 0 squared is 0. 0 squared is 0. Now at the negative 3 entry, I want to be a little more careful. We're going to square the number negative 3. In a calculator, you can get this wrong very easily if you're not careful. If you want to do it in a calculator, you're going to have to write negative 3 with parentheses around it, and then push the square button. It's the only way this will come out correctly, because it should be positive 9. In fact, when you're done with this column, it's a great idea to have a look at it and make sure there are no negatives along the entire thing. No negatives in the right column. Okay, it's worth writing down. Okay, so that completes steps 2 and 3, the deviations from the mean, and then the squared deviations from the mean. So the next step is to add up everything in this column. So sum all of these up. We'll write that right here actually. And what do we get when we sum these up? We have 1 plus 0 plus 4 plus 2 zeros plus 9, and that totals to 14. Okay, the next step says take this sum and divide it by n minus 1. Okay, so in other words, take that 14 that we have and divide it by n minus 1. So 14 is the value we calculated for the sum. Divide by n minus 1. Remember, n is 7. So this is 7 minus 1. It's 14 over 6. And I know that that's a non-ending, non-repeating, or it's a repeating decimal, but it's a non-ending decimal. So I'm not going to try to write it as a decimal yet. I'm going to pick it up because this expression is exactly what's inside this square root. So 14 over 6 is the number that we're going to put inside a large square root. So when we do that, 14 over 6, we're just taking a square root of this whole number. And a calculator, taking this out to 4 decimal places with a calculator first, 1.5275. And then I'll decide, maybe I'll round it further to 2 decimal places. That's always a safe bet. And typically what my lab asks for is things to be rounded to 2 decimal places. So 1.53. And that's it. That's the standard deviation. Now, it's not as obvious to calculate as the mean, but it's the closest thing that we've got to looking something like the mean deviation between data items on this list. So 1.53. Okay, so 2 more examples follow this. I won't work through these because it's very similar to what we just did, and the tables are provided. So students are encouraged to work through all the steps of each of these and calculate the standard deviation that's given. Note that the answers are here, so you can compare to that, at least rounded to 2 decimal places. If you get those, then you probably know what you're doing. If not, maybe consult the book or contact your instructor to help out. Alright, one last thing that we need to look at is knowing the mean and the standard deviation and comparing 2 data sets to that. So this example is a bit wordy, so let's start slowly and break it down. So our first paragraph through here, we read that suppose that 2 different tests designed by 2 different companies to detect a certain viral infection have been studied by an independent third-party laboratory to assess the accuracy of each test on multiple samples of patients with the infection, and suppose that the following results were found. Okay, so we have 2 different lab tests, or 2 different tests that we want to use to detect a viral infection, and then we've got a laboratory that's assessing these 2 different companies' tests for this infection. So Company A, starting the second paragraph, Company A's test had a mean detection rate of 95% among the patient group of positive cases. Let's write that down real quick. So Company A, their test, I'll just say the mean. The mean of their test was 95%. We had a bunch of different groups of patients, and on average, it was 95% accurate among these groups of patients. So, the next part of this is Company A's test had a standard deviation of 15% for its detection rate, or for its accuracy rate. Okay, it's accuracy. Just some explanation as to what these things mean in the problem. So its standard deviation was 15%. So in other words, from one group to the other of patients that this test was applied to, it had a 15% deviation in its accuracy rate. So let's compare that to Company B, and then we'll look at the question that we've got below. Company B's got some similar information. Company B's test among all the different patient groups, same groups, it had a mean accuracy of 90%. So 90% of the time it was accurate. Okay, now its standard deviation from one group to the next, standard deviation, that is given by, that's 2.5%. Okay, so mean of 90%, standard deviation of 2.5%. Okay, that's all the information of the problem. Now what are the questions? The questions were asked here, and this is just more or less a critical thinking question. There's not really much mathematics to do here. The first question is, which test is more accurate? Well, That one's probably pretty obvious. Which one has the better accuracy rate? So the mean accuracy of test A, on average, test A was 95% correct, and on average, test B was 90% correct. So it's pretty clear that company A has the more accurate test, just because of the mean. All right, so company A has a more accurate test. With mean detection rate or mean accuracy rate. It's a relative frequency, by the way, 95% compared to company B's 90%, right? 95% is higher than 90%, so it's a slightly better accuracy rate than company B. Okay? Now, the second question is, what test in a statistical sense is more reliable? So, when they say in a statistical sense, then how much variation is really what they're asking for. How varied can this test be? How wrong can it be, and how correct can it be? In some sense, or at least between among two different groups, or among multiple groups. So company B, when we look, the standard deviation comes into play here, 2.5% versus 15%. Company A's test, for whatever reason, seems to be varied all over the place. With a 95% accuracy, it was more accurate in some groups than it was in others, and it was a lot more accurate in some groups than it was in others, since it's got a 15% standard deviation. However, company B's standard deviation is 2.5%, and that being the case, it means that as the test was applied in the laboratory setting from one group to the next, it didn't vary much. So it's much more reliable as we transition from one group to the next. So statistically speaking, even though it's got a lower accuracy rate, company B has a more reliable accuracy rate. Accuracy since its standard deviation is 2.5% compared to company A's 15%. Okay, so in company A, if you could isolate the groups where the test did extremely well, this 95% that came out of here was probably close to 100%, then the test would be good among those groups. But if you're going to apply the test to a general population, well, company B's test with a standard deviation of 2.5% is really just going to be more reliable in terms of knowing whether or not how close you are to your mean of 90% accuracy in your testing. So anyway, there are a couple problems like this. They're more critical thinking than they are mathematical. One thing you might consider later on when we see the normal curve is how many standard deviations away from the mean certain values are. So in other words, if we took this 90% here, and then we were 2 standard deviations above the mean, we'd be adding 2.5 twice to 90. So 2.5 times 2 is 5. Add that to 90, and 95%. We could be that accurate, or we could be 2 standard deviations to the left of the mean, 90 minus 5, 85% accuracy in some groups. So we'll look at that more in the normal curve in section 6C, but for now, this is our basic comparison using the mean and standard deviation. So have a look at these problems, and good luck.